Hi everyone, in this video we're going to go over Lewis diagrams. Lewis diagrams, sometimes called dot structures, is one way to represent an element and its valence electrons. For example, sodium has one valence electron. So the Lewis dot structure shows the symbol for sodium, which is Na, with one dot next to it. So again, this one dot represents one valence electron. Now, we could write this a few different ways as well. We don't have to show it on the right-hand side. You could show it on the left, or up above, or down below, just as long as you show that one dot on one of the four sides of that symbol. So let's look at another example. Chlorine, we saw in the previous video, has 7 valence electrons. So the Lewis dot structure, or Lewis diagram, shows the symbol for chlorine surrounded by 7 dots. And notice that we only have 2 dots on a side. So we have 2 dots on the top of chlorine, on the right, on the bottom, and then the last dot is on the left. Now, we could have also drawn this with the single electron on the right, or we could show it on the top or the bottom, but we just want to show those 7 valence electrons as dots, and we can only put 2 electrons on a side maximum. Now, when we're actually drawing out a Lewis dot symbol, what I typically do is I start by putting one dot on each side first. Then, if I have any more electrons or dots, then I start pairing them up. And we'll see this as we go over some more examples as well. Now, remember, the number of valence electrons for a particular atom is given by the group number. So chlorine is in group 7, or sometimes this is referred to as group 17 if we're taking each of the columns into account. But if we're just looking at those representative or main group elements, then chlorine is in group 7, and that is the number of valence electrons. So let's practice. Let's draw the Lewis diagram for each of the elements in period 2 of the periodic table. All right, so if we look at our periodic table, the group is shown on the top, right? So we have group 1, 2, 3, 4, 5, 6, 7, and 8. And again, this is the numbering scheme if we're only looking at the main group elements, so the first 2 columns and the last 6 columns. So we're ignoring the middle, the transition metals. Okay, so this tells us how many valence electrons each element has. So let's start drawing the dots. So lithium has only 1 valence electron. So we'll just put 1 dot on lithium, and again, that could be on any of the 4 sides, but I'm just going to choose the right side. Now, beryllium has 2 valence electrons, so I'm going to put 1 on one side, and the second one on a different side. So I could have put the 2 dots on the left and the right, top, bottom, or just how I drew it. It doesn't necessarily matter, but they should be on different sides. Boron has 3, so we'll do 1, 2, 3. And again, those 3 dots are on different sides. And part of the reason why we're doing that is to show how many bonds the atom can make. So boron, for example, can make 3 bonds. And in the next chapter, we're going to see that it actually shares its 3 electrons with other atoms. So that's why we're separating the electrons for now. So let's look at carbon. Carbon has 4 valence electrons. So we'll put 1 on each side. So you can probably guess carbon can make 4 bonds. Now let's look at nitrogen. Nitrogen has 5 valence electrons. So we'll start by putting 1 electron or dot on each side. And then the 5th electron we can pair up with one of the other ones. So maybe the one on the top. So we have 2 electrons that are paired up. The other 3 are by themselves. So they're lone electrons. Now let's look at oxygen, which is in group 6. So it has 6 valence electrons. So we'll start by putting 1 on each side. And then the last 2 electrons, we can start to pair up with some of the other electrons. So we have 2 pairs and 2 lone electrons. So you can probably guess oxygen can make 2 bonds. Fluorine has 7 valence electrons. So let's start by putting 1 electron on each side, and then we'll start pairing them up. So this is actually going to look really similar to chlorine, right? Because chlorine was also in group 7. So fluorine has 3 pairs of electrons and 1 lone electron. And then neon has 8 valence electrons. So actually, we're going to end up pairing all of the electrons. So it has 4 pairs of electrons. All right, so now let's just say we're going down to period 3, so just below this one. This one has sodium, magnesium, all the way through to argon. So the Lewis dot symbols are going to look exactly the same as the period above. So sodium would have 1 valence electron, magnesium has 2, and then if we go all the way across, argon has 8. So hopefully you're starting to see the trend here with our Lewis dot symbols and the number of valence electrons that each atom has. Now, the reason why we like these Lewis dot symbols is we can better visualize how ionic compounds form and how the atoms are bonding with each other. So remember, sodium we saw earlier, because it has 1 valence electron, it can give up that electron to form a sodium ion. Similarly, magnesium has 2 valence electrons, so it can give those 2 electrons up to become like a noble gas and become a magnesium 2+ ion. We can also see fluorine, for example, just needs 1 more electron to have 8 total electrons. So that's the octet rule, right? And then we can see in group 8, the noble gases, they're already happy. They have 8 valence electrons. They don't need any more. So they're relatively unreactive. So let's see how we can use these Lewis diagrams to show the transfer of electrons when we're forming an ionic compound. So again, Lewis diagrams are very helpful when we're showing the transfer or sharing of electrons between atoms. So sodium wants to give up its 1 valence electron so that it becomes like a noble gas and has 8 valence electrons. So when it gives up its electron, it is losing a negative, right? So it's going to become positive. And then chlorine needs an electron to have 8 valence electrons. So it could gain that electron from sodium, and when it does, it's gaining a negative charge. So it's going to become a negative ion. And then we'll notice that sodium, since it's positive, is going to attract chlorine, which is negative. And they can form an ionic compound. And the way we write that ionic compound is NaCl. So notice that we don't show the electrons in the final ionic compound formula. We also don't show the charges because the charges will always be the same for these ions. Sodium will always be a positive 1 ion. Chlorine will always be a negative 1 ion. So we don't have to show their charges in their formula. They're just going to list the compound as NaCl. And again, this is sodium chloride. So remember, negative ions are going to have a different ending to their name. So instead of chlorine, it is chloride. Okay, so let's look at a case where maybe the charges don't match up between the ions. What do we do then? So some ionic compounds have different numbers of cations and anions in order for the positives and the negatives to match. So in those cases, electron transfer occurs between more than one atom. So for example, down below we have magnesium and bromine. And they're going to end up forming magnesium bromide, or MgBr2. So this little subscript tells us that we have 2 bromide ions in this ionic compound. And the reason for that is the charge of magnesium doesn't match up with the charge of a bromide ion. So we need 2 bromide ions in order to match the charge on magnesium. Because ideally we want our ionic compound to have 0 overall charge. We want all of our charges to match up. So again, we have magnesium, which has 2 valence electrons. So if it gives up those 2 valence electrons, then it will have 8 valence electrons like a noble gas. We saw that earlier in the last video. So magnesium ends up with a 2+ charge when it's an ion. Now, if we just focus on one of these bromines, so let's say the one on the left, bromine is similar to chlorine. It has 7 valence electrons. So it wants to gain 1 electron in order to become like a noble gas and have 8 valence electrons. So this bromine, if it gains 1 electron, will become Br minus, and again it will have those 8 valence electrons. But again, Br minus and Mg2 plus aren't going to match, right? In order for that 2+ charge to become or to be matched, we need 2 of these Br minus ions. All right, so again, magnesium is going to lose 2 electrons to become like a noble gas, and each bromine is going to gain 1 electron. So then we end up with magnesium 2+, and we have 2 1 minus ions from the bromide ions. And so that's going to give us, let's see, if we add those together, we get a 0 overall charge for the ionic compound. So that's usually our goal, is to try to match the charges so that the overall charge of the ionic compound is 0. All right, so let's just go over a couple of things here. So notice that the cation, which is the positive ion, is written before the anion, which remember is the negative ion. So in this case, magnesium was the positive, so it goes before bromine, which was the negative charge. Now, because most metals form cations, or positive ions, and most nonmetals form anions, or negative ions, formulas typically list the metal first and then the nonmetal. All right, so magnesium is a metal. Bromine is a nonmetal. So this is another reason why it's good to know some of those trends on the periodic table. So where are the metals? Where are the nonmetals? Because that's going to help us figure out what has a positive charge, what has a negative charge. So metals are going to have positive charges when they become ions, and nonmetals are going to become negative ions. I also said on the last slide that charges are not written in a formula. And then finally, the proper formula for an ionic compound always has a net zero charge, just like we talked about on the last slide. So the total positive charge must equal the total negative charge. Okay, so knowing all of these rules for ionic compounds, let's do some practice. So use the Lewis diagrams to determine the formula for the following. The first example is lithium and chlorine. The second example is calcium and fluorine. And the third example is aluminum and chlorine. So let's do the first one together, and then I'll have you try the other two on your own. So if we look at lithium, remember, was in group 1 of the periodic table. So it has 1 valence electron. And then chlorine was in group 7 of the periodic table. So it has 1, 2, 3, 4, 5, 6, 7 valence electrons. And I purposely drew it so that the lone electrons are facing each other because that'll be easier to visualize. So lithium, it looks like, can give its 1 valence electron to chlorine. And then both of these atoms will be much happier because they'll both resemble noble gases and have an octet of valence electrons. So lithium, when it loses that 1 negative charge, is going to become a positive 1 ion. So remember, when lithium is neutral, it has an equal number of protons and electrons. So an equal number of positives and negatives. So when it loses one of those negatives, now it has extra positives. It has 1 extra positive, or an extra proton if we want to be specific about what it is. And then chlorine has an equal number of protons and electrons, but when it gains an electron, now it has an extra negative. So it's going to become a negative 1 ion. So now we can write the formula, which is going to just show one lithium and one chlorine because their charges +1 and -1 match. So we just need one of each in order to have an overall 0 charge. So that would be our answer is LiCl. Now, you don't have to draw the Lewis diagrams if you don't want to. If you can already see what the charges are and you just want to match those charges up, that's totally fine. But sometimes it can help to see that visual using the Lewis diagrams. So pause the video, try number 2 and number 3 on your own first, and when you're done, you can unpause and we'll go over it together. All right, so let's look at calcium and fluorine. So calcium, which group is calcium in? Group 2. So how many valence electrons does calcium have? 2. Okay, and then fluorine, which group is fluorine in? Group 7. So it has 7 valence electrons. So let's draw those 7 valence electrons. Oops, I meant to put the lone electron on the left. I'll just swap these. So I'll put the lone electron there. Okay, so initially it looks like calcium could give one of its electrons to this fluorine so that it will have 8 electrons. But it can't give fluorine that second electron, right? That would be too many. That would be more than 8. So what we could do is we could draw another fluorine here with 7 valence electrons. And I'm going to just put the lone electron on the top. And calcium could give its second electron to that second fluorine. So the other way to think about this is if calcium loses both of its valence electrons to become like a noble gas, that means it's giving up 2 negatives. So it will have 2 extra positives in its nucleus. So that's a +2 charge for calcium. And then fluorine only needs to gain 1 electron to become like a noble gas with 8 valence electrons. So when it gains that 1 extra electron or that extra negative, it's going to be a -1 ion. So that +2 and that -1 don't quite match. We need an extra -1. So we're just going to multiply the fluorine, or the fluoride ion, I should say, by 2. So our final formula will be CaF2. And notice that I drew the 2 as a subscript. So that's how we can tell how many of each atom we have in our molecular formula, or ionic formula. So that would be our answer, CaF2. So again, you can always use the Lewis diagrams to visualize what your compound is going to look like. Or if you can already figure out the charges without the Lewis structure, you could do it that way too. So now let's look at aluminum and chlorine. So let's see, aluminum, which group is aluminum in? Group 3, so it has 3 valence electrons. And then chlorine, we saw before in the first example here, has 7 valence electrons. It's in group 7. All right, so let's just kind of jump ahead a little bit. If aluminum loses all three of its valence electrons to become like a noble gas, what charge would that create? So if we lose three negatives, aluminum would end up with a +3 charge because it will have 3 extra protons compared to the number of electrons, right? And then what about chlorine? If chlorine gains 1 electron to end up with 8 electrons, then it will have a -1 charge, which we saw earlier. So +3 and -1 do not match. So what do we need to do to make sure those charges match? We need 3 chloride ions, right? So we're just going to multiply the chloride ion by 3, and that will give us AlCl3. So that's another way to look at it, right? Without having to draw each Lewis diagram. Okay, are you ready for a challenge problem? So what is the formula for aluminum and oxygen? So try this one on your own first. It might help to draw a picture using the Lewis dot structures or Lewis diagrams. Or you can just try to figure out what the charges would be on each. And then when you're done, or if you get stuck, you can unpause the video and we'll go over it together. All right, so let's look at aluminum. So we just saw that aluminum has 3 valence electrons. So it wants to give up those 3 electrons to become like a noble gas. Because remember, if it gives up those 3 valence electrons, it will then have 8 valence electrons. And it's easier for aluminum to give up 3 electrons rather than gain 5 electrons, right? So aluminum will end up with a +3 charge. And then what about oxygen? What do we need to do to give oxygen an octet? We saw earlier oxygen is in group 6, so it has 6 valence electrons. So how can we give oxygen 8 electrons? Well, it would need to gain 2 electrons. So what charge would oxygen have once it has 8 electrons? -2. So it's gaining 2 electrons to become a -2 ion because we have 2 extra negatives. So again, aluminum is losing 3 electrons. So it becomes a +3 ion, and oxygen gains 2 electrons to become a -2 ion. So this would be the oxide ion, and aluminum is just the aluminum ion. All right, so +3 and -2 do not match. So how can we match those charges? Well, we could always draw a picture, right? So let's say we have, it looks like we need another oxygen at least. So let's draw 2 of these oxide ions. Okay, so we have +3 from aluminum. And now we have a total, if we add up the charges on the oxide ions, we have a total of -4. Okay, so now we have too many negatives, not enough positives. So let's add another aluminum ion. Okay, so now we have +6 from our aluminum ions, but we only have -4 from the oxide ions. So let's add another oxide. We need more negatives. Okay, so now it looks like we have +6 from our aluminum ions and -6 from our oxide ions. So now everything matches. So this will give us Al2O3 as our formula because we have 2 aluminum ions and 3 oxide ions. Now, another way that you could think about this is what I kind of do, I just multiply the atoms by the other one's charge. So aluminum +3, I'm going to multiply this by 2, which is the charge on the oxide ion. And then for the oxide ion, since we need to match aluminum's charge, I'm going to multiply that by 3, which is the charge on the aluminum ion. Oh, whoops. I highlighted the wrong thing. There we go. All right, so now that means we have 2 aluminum ions and 3 oxide ions. And that will give us our Al2O3 formula. So there's lots of different ways to figure out these formulas. If you're more of a visual person, you could just draw out the Lewis diagrams. But if you like the math part of it, you could always try to find that common, factor, multiply each ion by the other's charge, and that will give you the correct formula each time. Even if it's just multiplying by 1, right? It'll still give you the correct formula. Okay, so I think we'll stop there today. In the next video, we're going to go over some properties of ionic compounds, and then we're going to talk about a very special type of ion called a polyatomic ion. So I will see you in that video.